Hi everyone, as you come in, if you could put how many years you have been teaching math in the chat, that would be really great. So in the chat, just type how many years you have been teaching mathematics or how many years you have been teaching overall. So I've seen 5 years. Someone has says 5. Chat disabled, 29, 19, 23, 20, 23 years, 6 years. So well over, someone said 3 years, 2 years as math. Excellent. So we have well over 100 years of experience in this room with you guys. So you are the experts doing this already. And we are here to learn together to refine some of the things that we're doing already. Some of this you may have been already been doing, but it's great to kind of have a refresher, reassurance that you're doing the right thing. And for some of us, some of this might be new. My name is Dr. Jonté Myers. You could call me Jonté, and I'll be your presenter today. I'm an associate professor at Georgia State University, and my research focuses on mathematics instruction for students who struggle in math, including those with documented learning disabilities. Dyscalculia are also involved in that group, and those who struggle without any sort of identification of a disability or in any of the IDA categories as we do it in the United States. It's great to have you. I have compacted what I normally do in like an entire day into about an hour. So let's get going. There's a lot for us to do today. So, but without further ado, I have this problem on the screen. How many times, and you will type yes or no if you have seen this type of response from your students. Have you ever seen this type of response from your students when it comes to fractions? 1/2 plus 1/3 is equal to 2/5. Have you ever seen this? Yes. Someone said yes. It's a very common error. One in the research, one of the most common errors. So what they're doing, they are overgeneralizing operations with whole numbers to fractions. And I it's sort of one of the things that we grapple with in the field. How do we help them to see this concretely? Remember this problem as we go along. There are some other misconceptions that will talk about, but yes, you have seen this before. So what we are building today, we will understand why parts of shapes is an insufficient um, way to help kids understand fractions. We will identify five, we call them high leverage misconceptions and their conceptual roots. We will use a CRA. Many of you see it as a CPA, concrete representational abstract. In some jurisdictions or in some other countries, they say concrete pictorial abstract. You will see CVA, all these different things, regardless of the how they put it together. It's the same basic from instructional framework for helping students to understand mathematics. We will see how place value this early number sense skill that many of our students tend to have issues with can carry on to decimals and fractions and show how these two things are a unified system. And we will leave with about 3 moves that you can make tomorrow. Might be more, but let's get into it. So one of the biggest problems is that we taught fractions early in a somewhat ineffective way. Oftentimes, I remember as a child, when I first saw fractions, I saw them within a shape, like a circle. So a half or a third, I shaded shapes and that type of thing. I always saw fractions within the context of a shape, right? It's part of a shape. And then we looked at the bottom tells us how many pieces of we have in that shape, and the top tells us how many we have shaded or how many we have taken out of that shape. Students tend to keep their schemas tend to force them into thinking fractions only live within shapes. They are not numbers, right? They don't live on a number line, especially. And the number line, when we talk about early number sense, is one of the most powerful tools to help kids to really develop their mathematics thinking because the number line carries all the way from number sense up to calculus because they have to do things on the number line in calculus 1 and calculus 2 as well. So the number line is something that is so important. But oftentimes when we introduce fractions, we introduce them in the context of shapes. I'm not saying not to do the shapes, but to make the connection more deliberate with the number line, pairing it with the number line. Let's look at the first misconception. A fraction, this is one of the things that we were told. A fraction is the shaded part of a shape. I'm not saying that you have done this, but how many times have you seen this? Have you ever seen this? If you have, type the number one in the chat pod. If you have not, type two. Right. It's very common. We always talk about a shape when we talk about fractions. And students embed that in their minds, and it causes some problems down the road. As we said before, it's not a bad thing for them to see it in that way, but we have to take them outside of that into a more uh, what we'll say a general framework that carries in terms of the progression of mathematics. So what they can do is to identify and shade fractions in area models. Area models become very important. So shading fractions is an essential skill because area models, if we were to do this workshop for an entire day, you will see area models from the time you start till the time you leave, right? It passes the basic identification of fractions. Great for that. But what it cannot do for the kids is to help them to see 3/4 has a place on a number line. Explain why 3/4 is less than 1. Understand why 2/4 and 1/4 are the same number, right? And then make those connections to decimals. Because if I shade 1/2, there is no obvious connection to a decimal. There is no obvious connection to 0.5 being 1/2 when we shade. So they are not inherently bad. What we are saying is we have to redefine fractions and start placing them in a context that leads to a better understanding based on the progression of mathematics. So, great instructional move. Once you have gotten them comfortable with fractions in the shades, introduce the number line. Take those shaded parts and ask them and show them how it fits on a number line. And you could start with a number line with 0 to 1. Always start with 0. And I would even say put a negative number on the other side because that's, if you were to do the full workshop, you will see why negative numbers and understanding that they exist becomes very, very important later on. Oftentimes we teach kids about the one side of the track. Oh, they're only positive integers or positive numbers without them understanding, at least at that very age, that there are some other numbers over here that you are going to learn later on, but they do exist. And by how do we do that? Is to use the number line, start at 0, and even put -1 on the other side. And if they ask what that is, then you could explain to them that on that side lives some other type of numbers. We are not going to look at those. We are going to focus on this side for now, because that becomes very important later on. So what is a fraction? It's an area model. We could see how it looks in an area model like that, 3/5. It represents parts of a whole. It's an essential starting point. They see it, they could build it, they could touch it. It's great, but it shouldn't be where we live in terms of the instruction. We could show them as a set, right? In this way, discrete quantities. This supports all the meaning of numbers in terms of, representing fractions. You know, it's useful for ratios and proportions later on, but still no number line. The next thing we want to do is to show them that it is a point on a number line, the continuum. That now helps them to understand magnitude and position. Because if you start at 0, 0 means they will know that 0 is smaller than 1. So anything closer to 0 will be smaller than than a fraction that is closer to 1. So right there and then we're helping them to understand magnitude. And magnitude becomes one of those things that is so essential. The opening problem that we have is because many of them do not understand magnitude, right? It supports comparison of fractions or estimations. And this is where fractions live long term in the projection of mathematics, in the from arithmetic to algebra to calculus 1. That number line becomes essential. So the number line is not necessarily a more difficult version of the set model or the area model. It answers a different type of question. Where does this number live in relation to other numbers. And here is a classic number line, starts at 0. I didn't put the negative on the other side, but I should have practiced what I preach. And usually we start with 0 to 1, or we go up to 2, just to give a sense of where these numbers live. Students start to see that 1/3 is closer to 0, therefore 1/3 is smaller than 1/2. 1/2 is closer to 1, therefore 1/2 is larger than 1/3, right? And so on and so forth. 3/4 is larger than 1/3 because it's closer to 1. So fractions has a location. The location tells their magnitude. It has size relative to other numbers, and they can be compared, ordered, and estimated. So if I ask a child to show me where they will place, I would say 2/3, at least they should put it above 1/3. So we know that they are going to put it above 1/3. The next part is to help them to understand, should it go above a half or below a half? And that's a different type of discussion when it comes there. So if a student can only represent fractions within a shape, they don't know what a fraction is as yet, unfortunately. Again, I'll reiterate this. Start with the shapes. It's great for them to see it and experience it concretely. But that progression should take them up to a number line. So in terms of this question, what is the largest and how do you know? What procedures would you help a child to follow to know which fraction is the largest? What we do is to compare denominators, or we could put this on a number line, right? If they understand 0 to 1, 1 is the cutoff here. We put half of that. That's 1/2. Where does 1/3 sit in that? Where does 1/6 sit in that, right? A child might say, well, 1/2 is smaller or larger because it has a larger denominator. That's not enough for them to demonstrate their conceptual understanding, right? It's the unit size that we are thinking. So I usually ask them in this way. If I have one pizza and I split it between you and I, you get a bigger piece than if I split it between 3 people. So I take the pizza, cut it up with 3 people, and then is your part bigger or smaller? So they will see now you have 1/3 of that pizza, so you have a smaller piece. What if I divide it by 4 people, or 5 or 6? What happens to the piece that you get? The piece that you get gets smaller. So as you divide one unit by more into smaller pieces, it becomes a smaller fraction, right? So great way to demonstrate this is with fraction tiles. These things on the side are actual physical manipulatives. Many of you would have seen these before. How many of you have worked with fraction tiles in the past or currently works with them? Type Y for yes and type N for no. Right. Fraction tiles are your best friend. These are your best friend. Get some fraction tiles. You could make them yourself. There are some templates online. You print them, laminate them. If you buy them at Amazon, it's like $8, $9 a pop. But you can make them yourselves. They are like, if you Google fraction tiles, right. They have them virtually as well. You could get them, you could print them, laminate them. The kids could, you know, throw water on them and you could have them for another time. These are some of the most powerful tools that you could have in your arsenal. And when you're working with fraction tiles, I encourage you to keep the unit, that purple tile here in my situation, keep that as a reference throughout, right? And you will see why. So so you will give students these pieces of tiles, and then you could just ask the question, which is larger, 1/2 or 1/3? Or ask them to put them up, stack them in terms of their size, and look for patterns. So you are not, it doesn't always have to be in this explicit way that we teach this, right? They can see it, they can manipulate it, they could look for patterns, right? Give them these tiles and say, put these in order in terms of their length, right? Which is the largest? Which is the smallest? What do you notice? So these types of high leverage practices can help students to start to see and understand magnitude of fractions, right? We have one whole, and we are now breaking that whole into two pieces to get halves, three pieces to get thirds, and so on and so forth, right? So they are counting in this situation, students point to the reference bar, the unit, same numerator, one, everyone has the same numerator, not counting pieces, different unit sizes, different, the denominator defines the unit size. So the bigger the unit size, the smaller the fraction. The bigger the number of people that we have to share the pizza with, the smaller the piece that I would get, connecting it back to what we talked about earlier. So what questions would you ask? And you could put it in the chat part. What questions could you ask to help students explain why increasing the number of equal parts change the unit? I talked about using pizza. What questions you might ask, or what scenario might you present to a child for them to get this, to conceptually understand this magnitude of fractions? Anyone? And you could drop it in the chat pod. Legs of a relay. We usually talk about the pi, similar to your pizza example. Excellent. What is the smallest fraction? Great question as well. We always use food and use money too. They don't mess with their money. If I have $1 and I'm sharing it with two people, how would that work? If I share it with three, if I share it with four, excellent. So food, money, bar models. Someone said that if we increase the number of people sharing it, what does that mean about the size each person gets? That's a powerful question. That really wraps it up and helps them to see it quite concretely in front of them. I often ask about sharing a cake. Excellent. Food and money. They don't go wrong with those things. Excellent questions. So now it gets a little more difficult. In the past, what we just looked at, the numerators, and we love to use the vocabulary, as my good friend Sarah Powell will say, always use the math vocabulary. It's not the top number and the bottom number. It's the denominator and numerator. Numerator, denominator. Let me put them in the correct order. Always use the vocabulary, the math vocabulary, precisely, right? Do not substitute them. Repeat them over and over again so they get it, right? So it gets a little more difficult now because the numerator and denominator are no longer the same. So which is the largest? So now we have the problem. The unit size are different and the number of units differ. So direct comparison is not possible, right? So what's the logical move here? Equivalent fractions. We have to create equivalent fractions. We cannot, throughout math, even when we divide fractions, and I didn't show this today, but when we divide fractions, we create equivalent pieces if we are going to do it the right way. I know we do change and flip, but that's procedural. The conceptual side of that will ask, why does change and flip work? And it works because we are actually creating equal units, a shared unit for the fractions, right? By finding the LCD, the lowest common denominator. And I didn't demonstrate that today. I could probably demonstrate that in the next round. If you want me to show you that the next time, type yes, and I'll show you how dividing fractions actually requires shared units. Everyone is saying yes, so I'm going to put that in there in the next round. Okay, that will be something I'll show you. Instead of saying change and flip, I'm going to show you why change and flip works. So finding the LCD translates to dividing fractions as well, even multiplying. It's the same thing, but I'll explain those later, the next time we meet. So in this case, we have to find the LCD. Right? Someone talked about brownies earlier, food again. So I wanted to make sure that I noted that. So we have to find a common unit. So we have to look for common denominator. It's the smallest shared multiple, becomes that LCD, and we rename each fraction using the LCD. So that's the key here. So from our example, 2/3, 3/4, 5/6, we want to find the lowest common denominator. So what we do is to write the multiples of 3, write the multiples of 4, write the multiples of 6, and the first number that pops up as common in all three, That's another great way to look at it. How much of the whole is left? But many of our students who struggle in math may not see that part. The gifted ones are going to more than likely notice that quite quickly. But and that's a great point. But we start from the ground up and build that, because when it comes to what the progression of math, finding the LCD is going to be very important in that way, because the magnitude alone is not what this skill is addressing. It's addressing some other underlying skills that they're going to need later on. So I like this, Melissa, but for the context of what we're trying to do, build these skills, these foundational skills, it may not carry through. But this is a great point as well to help them to see the magnitude, no doubt, right? Great point. So how do we rename each fraction? And then for 2/3, we express it as something over 12, right? What that is, we find a common multiplier. It will be, in this case, 4. So that's how we ended up with 8/12. Same thing here. 3/4 is something over 12. What that is, we find a common multiplier. What must we multiply 4 by to get 12? We have to multiply 4 by 3 to get 12. Therefore, we have to also multiply 3 by 3. So it's a common multiplier that we have to find. And the same thing for 5, 6, we will get 10/12. How many of you have used this chart before? Type 1 for yes. This is a multiplication chart. How many of you have used this in the classroom before? 1 for yes. I would see all ones. Right. Oftentimes, and the second question is, oftentimes, many of us, after we have done with multiplication tables, we kind of just put it on the wayside. They have learned their facts. How many have you seen this in fraction, where they're finding the LCD? Have you ever seen it in that context being used for finding the LCD? Right. So we have a perfectly good tool that they have learned and would have likely mastered, and then we don't recycle it, right? From this multiplication chart, and this is a simplified one. I didn't put all the other things around it. At this stage, if they are more fluent in this type of thing, they should understand what it represents. If they don't, we could actually create a much more elaborate, one for them, right? But let's look at this one. Actually, we could find the LCD of 3 numbers using this table, using this chart. I stayed at 10 because here we have 3. We remember the numbers that we have were, let's go back, 2/3, 3/4, and 5, 6. So we will need multiples of 3, multiples of 4, and multiples of 6. So the 3 lane will give you all the multiples of 3. It's instead of them writing them back. 4 gives them all the multiples of 4. 6 gives them the multiples of 6. And then they will look for the common number in all 3. That gives them 12. So their LCD is 12. Now they can go back and apply that here again. So this multiplication chart is a very powerful tool to help students find the multiples of 3 digits. How would you feel if I tell you that we could also do equivalent fractions with this? Yes, we can actually use this for equivalent fractions. Someone just taught it. Yes. Here is another upcycling of this chart, this very commonly used chart. How does the structure of this multiplication grid helps us to find equivalent fractions? Look at it carefully. You can see the patterns in there. Look at it, reflect on it, and tell me, yes. Anyone see the patterns? If you see the patterns, type 1. For equivalent fractions, they're right in there. Excellent. This is something, if we have helped our youngsters to learn math and use this to help them with their times tables, their number facts, It doesn't just end there. It also translates. Let me show you. 2/3. Remember the LCD is something over 12. So we have 2/3. We identify 2/3 here. So we have our 2/3. And we know that something over 12. That something over 12 sits right there. It's 8/12. Find the right, find the right row, find the matching columns, and you're good to go. Let's do 3/4. 3/4. We know that they need 12 again in that column because 12 is the LCD. We know it's 9/12. We need some other equivalent fractions. What is another equivalent of 3/4? This is an equivalent, this is an equivalent, this is an equivalent, this is an equivalent. Now you can ask students, what do you notice? We are multiplying by the same common number, the same common factor. This is not a shortcut. We already showed them how to find the LCD and to use that to create equivalent fractions. This is where we want to take them, showing them that the equivalent fractions live in this multiplication tables that they see all the time. So by helping them to make those connections, they can see this every day. Right? Let's look at 5/6. That was the other fraction. 5/6 is something over 10. Let's do 1/8. 1/8, and you have seen the pattern. 1/8, so shade 1, shade 8. Give me two equivalent fractions of 1/8. The child can say, okay, let's go across. I'm looking at the ones. I can go with 4/32, or I could get fancy and go 9/72. It's 1/8. Any fraction within reason in this case, right? Because this is to build their foundations. Now they start seeing patterns. So if I need an equivalent fraction, what do? That's where you should want to release them to, right? Multiply the numerator and the denominator by a common factor, right? This is great for helping them to make those connections, and then they start to generalize this now to other contexts. So going up to 10 is not a bad idea. Some people might want to expand. They say you don't have to expand it. The expansion makes them dependent. This tool is to help them to make those concrete connections and look for the patterns in these numbers and then say, okay, here is what happens. So then the question is, how do we get from 1/8 to 4/32? We multiply the 1 by 4, or we move 4 places across, which means we multiply. So to get from 8 to 32, we are also going to multiply by 4. This tool is a very powerful tool to help students make these connections. And I see some people saying, thank you, because this blew my mind many years ago when I saw it too. Because we were taught with the multiplication grid, but it was not utilized in this way, right? So let's revisit our examples. Based on this, we will know that 5/6 is the largest because they have the same common unit, and now we could compare the numerators. So the key idea is this is not a new tool. It's a tool that we kind of like, after they finish with their whole number operations and learning their number facts, we throw it off to the corner. We can reuse this tool in this way, okay? All right, so we went back here. 1/2 plus 1/3 is equal to 2/5. We can expose this misconception quite easily. A child can see this when we do it the right way. Let me show you. So the child treated numerators, they overgeneralize. No unit understanding, do not understand magnitude of numbers, and to put things together in terms of fractions, they must be the same size. What's the instructional move? Your fraction tiles, grab those fraction tiles off the cabinet, bring them to the table. Let's show you how that would work. So this is the power of CRA. So we're going to just do the C. We could do it with the R as well because we'll just be drawing what we are building. So let's build it. Always start with your whole. Always start with your whole. I usually say put some Velcro and put the hole on the table. Don't move it. Always have the hole. So we are building one half, but we will start with one hole and then we'll put the half tile. We will model 1/3. Same thing. So we'll have two sets in this case, right? So this is 1/3. Combine the pieces. 1/2 and 1/3. If we help students to understand mathematically that when we are saying something is equal to, it means that it must be the same. So 1/2 plus 1/3 is equal to 2/5. That's the misconception. So if I put 2/5 on this on the table, they must be the same length. Here we are destroying that. The misconception is destroyed here because if they are equal, they have to be the same length. So by just bringing out your number tiles, you have addressed that misconception. Does this make sense? Questions? One, if it makes sense. Two, if you need some more clarification. Excellent. Right. By letting them physically build it, you don't even have to ask them, give them any sort of what we say. You could even let them discover it. And this is where discovery learning has a place. I'm not anti-discovery. I am more structured in terms of how I believe it should happen, right? This is more of a guided type of a discovery, right? Giving them these pieces and putting them within some structure to figure out that if you add 1/3 and 1/2, you can never get 2/5. And I would usually give that to them and then ask them to prove that this is not true using these tiles. You don't have to always ask them for the answer. Give them the incorrect answer and say, use the tiles to prove that this is not true. Or using the tile confirm whether this is true or not, or to prove it. So the misconception is exposed. What is the conclusion we expect them to come to? We simply cannot put 1/2 and 1/3 together. We have to make sure that they are the same unit before we do that. And then we could take them to this one. This is the instructional response. Take some tiles and create equal units, or go back to your chart and find the LCD or equivalent fractions of 1/2 and 1/3 because we have found the LCD to be 6. So the chart comes into play here again, and now they can put them together. The pieces line up equally, so now we know that 1/2 and 1/3 is the same as 5/6 because they are the same length. So this is length-based modeling. So they can count the 6 to find that the total is 5/6. And notice they are the same size so that we can combine them. This is actual physical tiles that you will use in this context. I have them on the screen because we are not in a physical room. But if we were together in a physical room, you will be building these things on your table. Questions on this? And some people, talk about, and there are some online tools that they could use as well, virtual tools. Some people say that, these things could put students in a situation where they become dependent. No, what we are saying, we are building foundations here. Gradually, we remove the scaffold so that students can do these things at the abstract level, look at the numbers, and just solve it abstractly. So we are not advocating that they live in the concrete or the representational stage. We are saying we can fade those supports so that they get to the point of doing it fluently at the abstract level. All right. So the instructional takeaways, what questions would you ask students to help them understand why these pieces cannot combine? Anyone wants to share? What is a key question that we can ask our youngsters to help them understand that we cannot combine unlike fractions when we are adding? Anyone? So one response and I'll be good. Because I know we're pressed for time, but I know you got a lot going. You had a long day. Excellent. Do we have a name for it? Is it okay to talk about equal parts? Excellent. If you use fractions bars, you can ask the student, can we tell just by looking at this model what the answer is? Great question. That starts to get their mind thinking, right? Priming their thinking. Excellent question. Metacognitive strategies that you're promoting there, Julie. Julia, thank you so much. Okay. So instructional move for kids who are struggling with that, start at the concrete level. With CPA, CRA, we usually advocate every child, I believe, should touch each level. Even the child that is working at the abstract level, they might be procedurally fluent, meaning I know what I'm doing, but I don't know why I'm doing it. We can interrogate that, not by asking them to solve simple problems at the concrete level, by asking them to prove, okay, prove that this is the answer or not using concrete objects. That's a whole different type of assessment for a child who's showing great promise or giftedness at the abstract level. We can interrogate their true understanding of fractions by asking them to prove things and justify things. Make sense? We do not have to always ask them for the answer. Give them the wrong answer or give them the right answer and then ask them to prove if this is okay or to check using these objects that this is okay. That helps even the ones who are showing great promise at the abstract level to get some understanding using the concrete. Okay. So we press them on unit size. Very important. Are the unit sizes the same? If the unit size are not the same, what can we do or what we can't do? And then from this concrete, we will move to we'll transition to representational. Rather than building them with their physical objects, they will draw them. Yep, they will draw the same representations using the fraction tile. They will draw the fraction tiles. Right? Yep, we're just like halfway down. Here's another one that student kind of gets into some trouble. So what is a student thinking? They're saying 0.625 is bigger than 0.9 because 625 is bigger than 9. We have seen this before. Type 1, if you have seen this before. Yes. Decimals, again, they overgeneralize again. So what they did, excellent. It's very common. So what they did, they read a decimal as a whole number. So with fractions, they're doing operations like they work with whole numbers. If they are very fluent in whole numbers, some students actually overgeneralize those concepts to fractions and decimals. And that's why they become so difficult because of a lot of what they learn do not translate or generalize. So they think that 6.625 means 625 hundredths or 0.9 means 9/10. Someone is already preempting this, Miss Anna. You're right. Place value. Yes. This place value chart takes them all the way from early number sense up to algebra. I'll show you. Look at this place value chart. I'll let you think about it I'll give you a couple seconds to think about it. Look at the structure of this algebra chart. You see exponents in here as well? If they see this, and I'm saying, if we introduce the place value chart in a way like this, right? We just cover up the ones that they don't need right now. So they will always know that there is more on this place value chart. Rather than just using one and then you add later on. Use one, then hide it and say they will get curious. What is below that, teacher? Oh, we are not there yet. I'll show you. So it's in standard form. It's in word form. It's expressed as an exponent. And you could put them in the order in which they will progress in. I would put the exponents probably last in this one. Right? It's a fraction. It's also a decimal. So this is a truer representation of what a place value chart really is. This shows the progression. The power exponent should have come later on. But this actually shows students that this place value chart that they learn very early goes all the way to when they start working with exponents. So making units, and then we are at the representational level. So when we use this place value chart, this sits in the representational lane, right? Not at the concrete. So now we have which digit tells us the most important information about size, right? Right there and then they should be able to see that 0.9 is 9/10, and 9/10 is greater than 6/10, right? That's the only digit that matters here. It doesn't just show the answer, it also shows them why in terms of magnitude of numbers. So in terms of your instructional moves, let them, when they're working with decimals, use this place value chart before you compare, and have them read it aloud. 9/10 and 6/10 is the first comparison. If they are the same, what do? I move to the next, to the 10th, to the hundredths column. And then I keep doing that and comparing those until I find a situation where one digit is larger than the other. Because this could, you could say this could have been 9.9 and 0.925, right? So then they would move to the next column until they get the answer correct. Okay. So more digits doesn't equal larger. And we could help them with money. We have $1, which is 1.00, and 25 cents, 0.025. If we don't put those zeros on the $1, they will see that a quarter is not bigger than a dollar. They would not mess that up, right? But if we could even put money, situate money within a place value chart, we can help these youngsters make these connections when it comes to decimals. Because no one will pick that 25 cents is bigger than a dollar. Exactly. And helping them to understand the why, right? The student who says 0.035 is greater than 0.4 is not necessarily careless. They're applying whole number reasoning to a different system of numbers. More digits for them means larger numbers. That is wrong. The system changes, and to help them expose those changes, we can use the place value chart. And decimals are nothing new. How do we show that? 0.47. If we go back to our place value chart, let's use this place value chart. 0.47, let's work with this. So we have 0.47, and the child puts, always let them put the decimal and the 7 here. So now we have 4/10, because we could represent this as a fraction. Because if we go back here, look at it, fraction. We just replace the 1 with the digit that is here. So this would be 4/10. And this is actually 7/100. See it? So they're connecting decimals directly to fractions. They cannot do that when they shade. Because if we have 4/10 here, there is no clear way that they could convert this to this up here. But with this place value chart, they actually can see that. So 0.47, let's go back to where we were, is the same as 4/10 plus 7/100. Now the next move, can we add these? We are generalizing now. So they would not be using the tiles. By this stage, they would have been able to notice we need to create equivalent fractions here, right? Because the denominators are not the same. We need the same unit size. So they will apply that and to get that 0.47 is actually 47 over 100. Does this sit? Because oftentimes when I did this, my teacher told me it's 0.47. Just move 2 decimal places to the right and then put it over 1 and how many decimal places you moved. And that's all I knew. But if I were able to see this, because I would have already been able to add fractions, it would have been much, much clearer. Help them make the connections between decimals. Listen, decimals aren't anything new. That place value chart is going to help them to see that. And I hope you have these slides. You could actually keep these slides, some of these, the place value chart that I have here. You could create one of your own, but this is just an example of how you could help them make those connections. In these situations, you could work with just the decimals and the fraction part of it. But again, helping them to make the connections across different grade levels. So someone said, this is David off. And Julia said this, yes, this is a great way to make fraction connections between connections, sorry, between fractions and decimals. David Alf said, yes, so this is the way that we do it, is to ask the student to verbalize. Excellent, right? Verbalize in word form and that type of thing, right? The slides are there for you as well. Use them. I have no problems at all with that, right? I want you to use them. So to add these fractions, we need a common denominator. Now the skill that they learned before, and by now they would have mastered that skill, comes right back here now. So now they can apply that skill, build on that skill, generalize that skill to other areas to see that the skills that they learned using fractions are still necessary in decimals, right? And this is the way that they convert decimals to fractions and to understand decimals themselves. Now let's think of how we decompose 0.125. Usually I'll give you your turn. I don't know, we don't have a lot of time, but just think of how you will decompose this. You could create some other examples, and you will have the slides to work on this later on. We have 110 plus 2 over 100 plus 5 over 1,000. The next question is, can we add these together? No, we can't. Why? We don't have a common unit. So what must we do? We must make a common unit by creating equivalent fractions of each of those. We did that. We have 125 over 1,000, right? And working with numbers that are familiar. When it's recurring fractions, it's a different type of a context. But here's a great place to start to get them. And then you could introduce that as what we call tension, right? Here is some tension. How do we approach this? And then we could ask them to simplify things here in that way. But if they stay at 125 over 1,000, I would be fine with that. And then we could talk about simplification later on, because we more than likely would not have covered that concept by that time. Okay. Again, it's nothing new. Decimals is not a new system per se from fractions. Decimals and fractions, they live within the same system. Here's another misconception. This is 5 of 5, so we are getting closer to the end. Some students have problems aligning things, right? So I know we're strapped for time. So they treat the decimal again like addition. They're not lining up things. Again, this is the power of your place value chart. The decimal points, again, is the boundary. So they didn't respect the boundaries here. And the instructional move, here we go again, the place value chart. Imagine they would have worked with the place value chart when they were working with integers. Excellent. So someone said we have different size graph paper, larger grids available for students to use to help them align their work. Excellent. Grids are great. I would say the place value chart, greater. Grids are good, but the place value chart is greater because they now see magnitude and not just an advanced organizer without understanding the magnitude of numbers. So the grids are great. I'm not saying that it's not a good tool, but the place value chart really helps them with magnitude. It's not just a chart. It communicates something based on where the numbers sit, right? So how do we do this? Here we have our place value chart. They will put the numbers in a place value chart like this, and then they will learn that only one digit sits in each column, right? Under each place value. So some of them might be tempted to put 11 tenths. This is not something that you wouldn't see. So if you have 11 tenths, here is an opportunity to teach them grouping, right? If you have 11 tenths, you have to trade 10 of those for a unit because they can actually see if they're using the algebra tiles, that 10 small bricks will give you 1 unit. So they could trade that to get an extra one here, and now they will add that. Because they will put 11 tenths, say, I'll be okay with it, but they have to continue by regrouping to get one full unit, one, and then the remaining 1/10 that goes there, right? And here are some questions that we must ask. Why must the decimal points align? And these are questions that you could ask the students. What does alignment actually mean here? Alignment means that these numbers are the same magnitude, so we have to pair them together. So these are within the same, not the same magnitude, sorry. They have the same common denominator in that case if we are turning them to fractions. So we have to put them together in terms of the place value. These have the same, they sit in the same column in terms of place value. And a question we could ask here, which of these is larger before they even get going? Help them to understand the magnitude. Okay, we start at the ones. We know that 1 is greater than 0, so this has to be the larger number. Okay. So the instructional framework that we promote to help kids with this is to start at the concrete, build it. Fraction tiles, base 10 blocks, algebra tiles, counters. It helps students to see structure. At the representational models, number lines, area models. Those are the two that prominently, and the place value chart. Those are the three that prominently move across. I can show you how area models become an integral part of teaching polynomials, multiplying polynomials later on. So these skills that we are building down here, the area model is great for multiplication of whole numbers. If we are multiplying 20 by 42, we could do that using area models. And I'll show you next time how we could use an area model to do polynomials. Some of you in here might be at higher grades, but I'll show you that as well. And at the abstract level, this is where we want them to be. That's where we want them to be. All of us. We want them to be at the abstract level, understanding math conceptually, however. Because I can be at the abstract level and I'm procedurally fluent. I know how to do it, but I don't know why I'm doing it. For example, you give me 1,000 of these. You give a child 1,000 of these, and they will do change and flip and get 1,000 of them correctly. Ask them why it works. They'll be like, I just change and flip. Procedural fluency is not a clear indication of conceptual understanding. And what we are promoting is conceptual understanding. So we want them here, but we want them here conceptually, right? We want them to be working abstractly and understanding stuff conceptually. And sometimes when we are fluent here, take them back to this position. Do not force them to, I would not take a child back to this position by asking them to solve problems in that way. I would ask them to interrogate or proof or plan something to prove that this is or isn't an answer. Different type of assessment, flip the assessment. Before you leave, here are some things that you could do. Put fractions on a number line before you put them in a shape, right? And I know many of you, I'm preaching to the choir, but your colleague across the room, they might need to hear this, right? The young teacher that is coming in, that you are mentoring, they start, yes, put it on a number line before you put it into the shape. I would say put it in a shape and then the number line. Either one works, but the number line must be helping them to make that connection. So I would say put it in a number line as well as in a shape. I would reframe this if I had a thought through it a little more. show place value. Keep that place value chart. If you want to cover up the extra rows with the information, you can do that. And then make them malleable, Velcro, cover things up, use tape, but let them see that there is always something else that comes. And I would even expose them to it as well. You don't have to cover it up, expose them to it. They will ask questions, and then they will start to make those connections. They'll say, oh, I saw this in Mr. Capro's class. Yes, I saw when I'm doing exponents, it's the same system. Or I saw it in Julie's class. So great to keep that place value chart. Encourage them to use it. And then use the multiplication grid. Not as a replacement for instruction, but as a reinforcement tool. You have used this before. You know how to use this. Many of them will even create it or see it. Use that multiplication chart to help them to see the patterns in when they're doing the LCD and finding the equivalent fractions. It's a powerful tool, as you would have seen today. So what did the student believe? They didn't have an understanding of magnitude, right? Fractions have a position. They have a size relative to each other. And the pieces must match before combining them. And the next round, I'll show you that the pieces, if you want to understand division of fractions conceptually, the pieces must match before you divide them too. The error that we see when students work is not sitting with that problem at that point. It's another concept that they didn't learn. This child did not have a strong understanding of magnitude of numbers, equivalent fractions, and these type of things. So that's why we have to build those foundational skills before we start operations. Questions? If you have any questions for me? No, we are pressed for time, but I'm here to answer questions. Yeah, when you come the ratios, yeah, we're doing that next week. I would do some of this next week. Not the next time, for sure. So let me pull this. I'm gonna take this comment and put it in my notes. Let me put it in my planning notes so that because my goal was to build the next set of slides based on the response today. Because it's a little tougher to plan for this because I usually do this in an entire day. So I wanted to see how this will fit in 1 hour. Miss, what strategy would you use for converting between different forms, specifically these 37 tenths, 9? You could use a place value system, or you could use the algebra tiles. The algebra tiles that shows 37 tenths, they will have like the rods, the flats, and that kind of. They could actually build them with their hands, and then they could start comparing the sizes. Because if you have 37 tenths lined up, right, you could see that at least 100 could fit several times in that. So use those algebra tiles, right? Somebody has a hard time connecting fractions and divisions. Unfortunately, I will be able to join next week because I think there might be a recording available, Julia, so we could contact the folks here and the great folks who organize this workshop, and we could go from there. But otherwise than that, let me finish up. Don't go yet. Let me finish the slides. And so questions, we have that, and then what this might look like in a setting. You could reflect on these questions. My email is available as well. I'll put it in the chat. You could shoot me an email and I would respond. So again, here's my email here. So thanks to you for your engagement, for the great work you're doing to make sure our scholars have great mathematics instruction. Heartfelt gratitude to the Windward Institute for this partnership and their dedication to evidence-based practices. And don't forget the summer workshop. I'm doing one on word problems in the summer. It's going to be exciting. It's going to focus mainly on the multiplicative schemas and what happens when the schemas no longer fit. So we have word problems when schemas don't fit. What should we do? We throw our hands up? No, there is a strategy that works for that as well. Thank you for being such engaging participants. I truly appreciate your your indulgence and your support. If there's anything we can improve on, just let us know. And I'm looking forward to the next time that we meet. Thank you.